Okay. Okay. Good morning and good afternoon to the audience in UK and China. First of all, I would like to thank the organizer to give me this opportunity to share, some of our recent results and AI-based sensing and imaging systems. I'm Zhong Tang from the Chinese University of Hong Kong in Shenzhen. So before my talk, I will define some of the acronyms I'm going to use in my presentation. So the first one is AIE. AIE stands for aggregation-induced emission. And if a luminogen has this AIE property, I will call it as a AIEgen. So this is the outline of my presentation. First, I will, talk about the AIE processes and how it works. We know that the fluorescent bioimaging is very important. According to the Nobel Foundation, this kind of technique enables people to watch processes that were previously invisible. It's very important because it's also very unique because it can offer in vivo, on-site, and in-time information, and not only biological structures, but also biological processes. Because of this, if you still remember, the Nobel Prizes in chemistry have been, awarded to the people working in the area 2 times in 2008 and 2014. So, in some sense, this is a very mature area of research. However, it still has some bigger issues, okay, to be tackled. So here I'm going to talk about one, very difficult issue people have faced for centuries. We know that in bioimaging systems, fluorophores actually are utilized as biosensors or bioprobes in aqueous medium because the liquid medium supporting life basically is water. However, the fluorophores that emit light actually are very often hydrophobic organic molecules. Because they are hydrophobic, they are incompatible with water. So you can think about putting a drop of water, putting a drop of oil into water. What will happen? Okay, so basically oil will form oil droplets. It will not be dispersed in water. Okay, similarly, this kind of hydrophobic fluorophores will naturally aggregate when you put it into the aqueous medium. The problem is that when the aggregate is formed, the light emission from the fluorophores are often weakened and sometimes completely quenched. So this is a so-called aggregation caused quenching or ACQ effect, which has bothered people for more than a century. We say seeing is believing. I give you an example of this kind of ACQ system. You can see this molecule is named pyranine. It's a typical hydrophobic organic compound. When it's dissolved in an organic solvent at low concentration, when you irradiate with UV light, it will emit, bright blue light very efficiently. However, if you add water into the organic solvent, okay, at 80%, water is weakened. When the water fraction is further increased to 90%, okay, now the aggregate of the parent molecules will not emit light anymore. Okay, so this is so-called aggregation caused quenching or ACQ effect. Obviously, this is very harmful to bioimaging applications because when you inject this kind of solution into cellular system, the molecules will form aggregates and emission will be quenched. So you don't see any signal at all. People have tried to solve the problem, but with limited success. About 20 years ago, we observed anti-ACQ phenomena. You can see this molecule is very strange. Okay, it's soluble in many organic solvents. However, if you use UV light to excite the dilute solution of this molecule in an organic solvent, you don't see any emission at all. Now, if I add water into organic solvent at 80% of water fraction, the molecules of this compound will form nano aggregates. Now, if you excite it with UV light, you see very strong emission. And the more water add, the more aggregate formation, and the stronger the emission. Because in this case, the molecule species doesn't emit light, but its aggregate can emit light. That means the emission is induced by the aggregate formation. So we call this phenomenon as aggregation-induced emission, or AIE. In this PPT, I will use this video to explain you how this AIE process is working. Okay, so here I discuss about the magnetic picture. We know that everything is in the ground state, okay, at the normal condition. Now, if you excite the molecule with photonic energy, the molecule will absorb energy and will jump to the excited state. In the excited state, of course, the action is not stable. It must come back to the stable ground state. And when it comes back, it will go through this channel. If we assume this water flow is light beam, that means this is a radiative decay. Then you will see very strong light emission. However, there's another channel here, another pathway here. So you can see that the energy of the water flow is converted to mechanical energy by the moving of this wheel. Okay, so the mechanical energy is non-radiative decay. Okay, so if this pathway dominates, then too bad. You will not see net emission because the photonic energy is converted to another form of non-radiative energy. However, if we block this channel, okay, the extons will come back to the ground state through this channel, that you will see very strong emission. Okay, so now let's see what happens to our molecules. This molecule is named tetraphenylethanine, in short, TPE. And this molecule actually in the excited state, the double bond is also open because this molecule can undergo 6 times isomerization. Okay, so the double bond must be open, and once the double bond is open, the whole molecule will rotate like crazy. Okay, so this means, this exton will come back to the ground state through this channel. So that's why you don't see any emission in dilute solution. However, when the molecules are aggregated, now this kind of a molecular motion becomes difficult. Okay, so that means you block this channel, the molecule will come back from this pathway, so you will see very strong emission. So here basically is the restriction of intramolecular motion, or RIM, that is responsible for the AIE phenomena we have observed. Okay, so according to this RIM mechanism, we have designed hundreds of these kind of molecules. Okay, so the structure features that these kind of molecules are active in either vibration or rotation. Okay, so we can now have all different color of emission, from blue to green to yellow to orange to red, and actually we can go to near IR. Okay, the longest wavelength we can accomplish now is about 1,700 nanometers. Okay, quantum yield, sometimes we can have almost unity or 100% quantum yield. Okay, now if you still remember, for pyramid, the nanoparticle suspended in water does not emit light. However, you can see this is our nanoparticle suspended in water. It's very, very emissive. That means these kind of nanoparticles are very useful for biosensing and bioimaging applications. and the solid powders are also very emissive. So this make our AI genes very useful for the fabrication of organo-optoelectronic devices such as light emitting diodes. Okay, so because our aggregates are very emissive, and if you think about it, actually light emitting materials are commonly used in the solid state or as nanoparticles. Okay, so our AI genes can be utilized for optoelectronic applications such as smart materials, light emitting nuclear crystals, and efficient organic light emitting diode. It can also be utilized to make a solar cell waveguides and monitor for invisible processes. It can also be utilized as a chemical sensor to imaging all kinds of chemical species. Okay, so basically the design principle is very simple. If you design the rotor that can bond with the ionic species, okay, so you restrict the molecular motion, then emissions turn on. So okay, so in doing so, you can have very specific sensing systems. We can also visualize bacteria and also viruses, and we can visualize the fingerprint and examples of biomedical applications of our AI genes. Actually, in the market, there are many of these kind of organelle staining dyes commercially available. Okay, you can see there's ER tracker, okay, metal tracker and natural tracker, but it doesn't matter what kind of tracker. You can see the common feature is that in the solution state, the emission is much brighter than in the aqueous medium. Okay, and our system is different. You can see our AI gene is not emissive, okay, when it's dissolved, but in the aqueous medium, the emission is very, very strong. You can see that this nail red solid powder is not emissive, but our AI gene powder is very, very emissive. Okay, now let me give you some examples of that, the organelle specific AI biosensors. You can see this is a mitochondria specific system. We can image the mitochondria in very high resolution. We can see all these, tiny, fine structures. Not just the image in itself, we can also tell you how the membrane potential is changing. You can see this is a normal membrane potential. And if you use a drug called oligomycin to increase the membrane potential, you can see the emission will be, brightened. Okay, will be brightened. Now, if you use the CCCP drug to decrease the membrane potential, you can see the emission intensity is decreased. Okay, so even more amazingly, we have a very simple, not just one, we have many AI genes which can image cancer cells, but not normal cells. You can see these are all cancer cells, these are normal cells. So they are pairs. Okay, you can see the structure actually is very simple. Here we did not use any antibody antigen interaction. Okay, we just incubate our AI gene with this kind of cancer cell and the normal cell. Okay, and the result is that all these cancer cells will emit light, but normal cell will not. Actually, the reason is very simple. If you still remember the previous PPT, I have talked about the membrane potential change. Okay, so basically the difference between cancer cell and the normal cell is that the cancer cell has very active metabolism. Okay, so that will make the membrane potential very negative. And also because it's a very active metabolism process. Okay, cancer cells have more, okay, mitochondria in number. Okay, so both of these two factors will attract our positive charge AIEgen to the cancer cell, okay, to internalize and to accumulate in the mitochondria. Okay, so for our AIEgen, the more the aggregates, the stronger the emission. So that is why eventually the cancer cells, become very, very emissive, much more emissive than the normal cells. So this will enable us to easily differentiate cancer cells from normal cells. Okay, so the previous example is about the mitochondria. Now I will talk about the cell membrane. Actually, in the market, there are many these kind of dyes. Okay, however, you have to incubate, you have to control the temperature, and the most important thing is that you have to wash. Okay, you can see this AIEgen, you just mix it, you just put it into the incubation cell after 3 seconds, okay, at room temperature, without washing. You can see the cell membrane. Actually, this is very easy to understand because you see this molecule has 2 charges, so it's water soluble. Remember, okay, our AIEgen is not emissive when it's dissolved. So when it's dissolved in water, you don't see any emission. However, when it bound to the cell membrane, when it's stuck, okay, to the membrane lipid, okay, so the molecular motion becomes difficult. Now the IIM mechanism will come into play, so you will see the emission. Okay, so that is why you don't need to wash, because we don't have a background emission. Okay, so the next example is about the lipid droplet. And you can see body part actually is specific to lipid droplet. You can see our AIEgen imaging and body part is very similar. Okay, but however, our system is much better than body part because you can see when you do the scanning with the body part, okay, the emission will become weaker and weaker and weaker. Eventually, everything will disappear because of the photobleaching. Okay, photooxidation induced photobleaching. But for AIEgen, you can see there's no such degradation. Okay, you can always see very strong emission. And we can also have this so-called photoactivatable AIEgen. You can see this molecule initially is not emissive. However, if you irradiate, it will undergo photooxidative dehydrogenation. Okay, so this will become conjugated and the emissions turn on. Okay, you can see here, initially no emission, without irradiation, no emission. But once you irradiate for about 20 seconds, the emissions turn on. Okay, the longer the time of the irradiation, the stronger the light emission. Okay, so this will enable you to do so-called localized high resolution imaging. Okay, so when you just irradiate here, you will see the emission here, and if you irradiate spot 2, you get the emission here, and then this for spot 3. And we are now very much interested, to search, AIEgens from biological systems. Okay, so this is a Chinese medicine called berberine. Okay, in Chinese it's huannianshu. And you can see this molecule is AIE active. The solution is not emissive, but the aggregate is very, very emissive. And the working mechanism is still IIM. Okay, because when you incorporate it into this CB ring, the emission is turned on. Okay, and because this molecule is positive charge, and we can utilize it for DNA detection because DNA is negative charge. So the electrostatic interaction will make this complex. Inside the complex, the molecule cannot move and emissions turn on. And if you still remember, okay, the positive charge AIEgen cannot enter the normal cell, but however, you can enter the cancer cell. Okay, so inside the cancer cell, it will generate a reactive oxygen species. That's so-called ROS. The ROS will activate photodynamic therapy. Okay, so it will kill the cancer cell. Also, the bacteria and the normal cell is different in terms of again, membrane potential. Okay, so when we mix normal cell with bacteria, the AI gene will enter the bacteria and eventually kill the bacteria. Okay, so this is this so-called diagnostic system, because it can do that diagnosis to tell you whether your body has bacteria, harmful pathogenic bacteria, and meanwhile it can kill the bacteria. Okay, so in the previous PPT, I told you that our AI gene can stain all kinds of cancer cells. But sometimes clinic doctor will ask me, hey, Dr. Tang, I just want to see one specific kind of cancer cell. I don't want to see all the cancer cells. Yes, we can do that. Okay, so we can do the bioconjugation with antibody, specific antibody. Okay, and if we use a water-soluble antibody, the bioconjugate will be dissolved in water. You will not emit light. However, the antibody-antigen interaction will attract our AI into the specific cancer cell. And here you have this so-called receptor-mediated endocytosis to make the bioconjugate internalized. And inside cell, in the lysosome, okay, the antibody is decomposed. So what left will be our hydrophobic AI gene. It will form an aggregate and emission will be turned on. Okay, so here, this is a commercial system, antibody site 3. Some of you probably have used it. And you can see when you put this commercial conjugate to the incubation system, you can see everywhere is emitting. Okay, so the cancer cell will change the color a little bit, and the brightness will change a little bit. So if you want to do high resolution imaging, you have to watch the unstained dyes molecules, the dye molecules. Okay. However, for our system, because as I just mentioned, our antigen bioconjugate is water soluble, so outside the cell there's no emission. Okay, it will only emit light after it is internalized. Okay, so by doing this, we can realize this so-called wash-free imaging. Okay, sometimes people want to do this long-term tracking, because say for example, you want to know whether the cancer cell will migrate inside the body from one organ to the other. Okay, so here we again do the bioconjugation. This is the AI gene called TP. I have to talk about that. Okay, tetraphenylethylene. So this is a very simple chemical reaction to attach it to a biopolymer called chitosan. And this bioconjugate will enable us to monitor cancer cell for up to 15 passengers. And we have some other system to enable us to monitor the therapeutic process. You can see this, we can use a stem cell to repair the broken leg of this mouse. Okay, you can see we can monitor the process up to 42 days. Okay, so this is this is very useful. And sometimes some people will ask me, can we easily attach AI genes to the object we want to monitor? Yes, we can do that. Okay, you can see in the bioconjugation area, there's a so-called click technique. The conventional click system requires people to use metallic catalyst, commonly copper. Okay, as you know, copper is toxic, so that is not good. That's not it's not suitable actually for biological systems. So here, what we do is that we use this carbonyl electron withdrawing group to activate this triple bond. Okay, and this activated triple bond now can react with bio systems without the pre-functionalization, because for the conventional clinical reaction, you need to do the pre-functionalization. You need to convert this amino group to AZ, or you have to attach an AZ group to the bio, object. Here we don't need to do that. Okay, we just mix this with a conventional system. We don't need to use metal, and we don't need to heat it up. Okay, just room temperature. You mix them together, and immediately this AIE gene will be attached to the bio object. Let me show you a few examples. You can see here, this BSA is a very common protein. Okay, now mix them together for a few minutes, and this AI gene will be attached to the BSA. You can see BSA before bioconjugation, it does not emit light. However, after bioconjugation, you can see now the protein becomes emissive. Okay, and we can also mix our AI gene with cell. You can see just for 2 minutes standing, the cell will become emissive. Okay, and we can all do the same thing to bacteria. You can see this bacteria. After you mix our AI gene with bacteria, the bacteria now become emissive. Okay, so this will enable you to see, first of all, whether inside the body there's some pathogenic bacteria, and secondly, you will know the location, and thirdly, you can monitor how it moves inside the body, right? So this make life much easier. Okay, so now I will talk about the so-called biomodernity bioimaging. Here, what we do is that we prepare this core shell nanoparticle. The core is inorganic nanoparticle, and the shell is our AI gene. Okay, so I will not go to detail, but just to tell you that you can clearly see this core shell structure. Okay, and you can see the thicker the shell, the stronger the emission. And this is very important. Okay, this is very important. Why is important? Because if you use conventional AI gene, you can't make this kind of organic-inorganic hybrid, because the inorganic core will quench the emission of a conventional fluorophore. You cannot make a very thick shell here, because once the shell is thick, the ACQ effect will quench the emission. When it's thin, the nanoparticle will quench the emission. When it's thick, the ACQ effect will quench the emission. However, for our system, we don't worry about that. Okay, although the interface, okay, the emission here is still quenched by the silver nanoparticle, but the outside, okay, can emit light. So that is why, if you remember, that is why when we increase the thickness of the shell, the emission will become stronger. Okay, so by doing this, we can have this dark field image. We can have this CT image. So we combine 3 sets of imaging together. We will not make mistakes. Okay. And in this area, people like long wavelength emission, and this is easy to understand because so far I have talked about visible emission, visible light emission. And if we go to longer wavelength side, okay, from 700 to about 1000 nanometer, this is so-called near R1 region, and beyond that, that's near R2. Okay, so near R2, near R1 and 2 are both better than visible light emission because the background becomes weaker. However, you can see when you compare these two, near R1 and near R2, near R2 is much better. You can see the resolution is much higher, and also when the wavelength is longer, the penetration depth will be better. Okay, so here we try to make such AI genes which can emit in the near R2 region, and you can see this molecule can give you very very fine imaging. you can see the resolution here is really high. And this is ECG people often use in the hospital. This is FDA approved, okay? But if you see the image, this is no comparison to our system. The resolution here is really poor, but our system, you can see, is really good. And as I just said, okay, when the wavelength is long, you can do, you can see much deeper. Okay, now you can see this is the mouse brain. Okay, we can go to 800 micron, and at this kind of depth, you can still see these kind of fine structures. And we can also differentiate benign tumor from malignant tumor. Okay, so what is the difference? For the malignant tumor, it has a lot of this kind of a nano pores. Okay, with see for example, this is the malignant tumor, and this is the blood vessel. Okay, so there's a lot of nanopores between these two entities. So that is why these cancer cells can enter your blood vessel, and it will migrate in through your whole body. Okay, so we utilize this feature. We inject our nanoparticle into the blood vessel of the mouse. Okay, and if we see very clear, okay, we know this is the tumor, but you can see that the picture here is very clean. That means that this is the benign one. However, with malignant, you can see that there are a lot of nanoparticles outside of the blood vessel. Okay, because of the nanopores enable our nanoparticle to come out from the blood vessel. Okay, so for by doing this, you can tell which one is malignant, which one is benign. And for the ER hello?
Hi there. We can hear you now.
It's okay?
Yeah, now it's fine. We can again see the image.
Okay. So, the excitation actually is also very important. So here we use this, utilize this 2-photon process. You can see we use a very long wavelength, 1,300 nanometer, to excite the AI gene. Okay, and it will come back to emit at about 810 nanometers. Okay, now you can see here, if you use this long wavelength to excite, you get a very strong signal. But if you use short wavelength to excite, that the signal is very weak. And also this long wavelength excitation enable very deep penetration. So you can have this 3D imaging of the mouse brain structure. Okay, here I've used this 2 video to demonstrate the advantages of our AIEgens. You can see there are 2 syringes here. This one you can see the light emission. That's the commercial system. Okay, the solution is emissive, and this is our AIE system. Our AIE, okay, as I emphasized many times, our AIE solution does not emit light. Now, if you inject to the mouse body here, okay, and the luminescent dyes, the fluorescent dyes will aggregate. Okay, so here our aggregate is very emissive. This aggregate is not emissive, and actually when the time goes by, this will become weaker and weaker. Now, let's see here. We want to see the interior structure of the mouse, but we don't want to open its stomach. So what we do is that we inject our AIE nanoparticle through the tail of the mouse. Okay, and as you can see here, without open stomach, you can see the interior structure. Okay, because there are emission. Now you can see after about 4 minutes, you can see this emission is almost gone, but this emission is still very, very bright. Okay, so people, often ask me, Dr. Tang, is your AIEgen biocompatible? Is there any toxicity? Okay, so we did, this toxicity test. So what we did is that we mix our AIEgen nanoparticle with the food of the mouse, and they just feed to the mouse. Okay, you can see that's a control group and an experimental group. You can see after 10 days feeding, you can see basically, there's basically not much difference between the experimental group and the control group. And this is the, after we sacrifice the experimental, animals, and we did this actually study, you can see basically everything is normal. And these are some biological, parameters. Okay, you can see the control group and the experimental group. There's not much difference. And another thing is about clearance. Okay, so the lifetime in the blood is about 4 hours. And you can see when you inject another particle to the mouse body, initially you can see, emission, okay, from the organs of the mouse. But after 1 day, 2 days, and 10 days, you can see everything is, is clear in the body. So it will not accumulate, and it will not, just maintain inside the animal's body. Okay, now the bacterial or the virus detection is a hot topic because of this, COVID-19 pandemic. So here we make this kind of AIEgen. Of course, we don't have access to COVID-19, so we use another bacteria in collaboration with Dr. Zhong in the CDC of Shenzhen. Okay, so this is the ELISA process. I will not talk about it. Okay, you people know this is a very common process, and we use our AIEgen to give you fluorescent signal, and we also have the color change. Okay, so this is the absorption. This is the emission. Now you can see that normally, as you know, for virus detection, people use this PCR, okay, to do the DNA analysis, which of course is very good, but it takes time. Okay, now for our system, we don't need to do the magnification. We don't need to do the PCR. Okay, reaction. So you can see without the bacteria, the color is kind of pink, okay, no fluorescence. However, if we have a bacteria, the color will change from pink to golden yellow, and the emissions turn on. Okay, you can see that the result by our AIEgen is 100% accurate. It's in perfect match with the PCR, results. Okay, so recently, in collaboration with a doctor in Shenzhen Hospital, we try to utilize this exosome, okay, because currently many people are interested in exosome. So Dr. Li got this exosome, from a cancer patient, and so we make this kind of a nanoparticle. Okay, so the inside nanoparticle is our AIEgen, and the AIEgen is wrapped by the exosome. Okay, and so if if you inject this nanoparticle into the body of the mouse, this exosome will serve as a targeting group to bring our nanoparticle to the tumor site. As you know, the tumor is oxygen deficient. Okay, so we use this drug to improve the situation. Okay, now after you use this drug, you will reduce the intratumoral tumor hypoxia level, and now so you have oxygen inside the tumor. Now, if you use UV light to be excited, and it will generate ROS, reactive oxygen species, and that will kill the tumor cells. Okay, you can see the ROS here, that will kill the tumor cell. Okay, so this AIEgen will serve as targeting function group to enable us to do so-called specific diagnostic process. You can see this is the data. Okay, so we implant the cancer cell to the mouse, and then we inject the nanoparticle, and then we do the PDT, and after about half a month, you can see the tumor cannot grow, and you can see that's the result. All the tumors are killed. Okay, let me summarize my talk by comparing our AIE system with the ACQ system. ACQ is the conventional system, AIE is our new system. So in terms of response, our AIE system is often turn on response. Okay, so that means without reaching the target, you don't see any signal. So there's no background emission. When you combine with the target, the molecular motion is restricted and emission is turned on. Okay, but for ACQ system, sometimes it's turned on, sometimes it's turned off. Okay, so to turn off actually is not good, because you have to turn everything off, then you know what happened. Okay, so turn on is much more sensitive than the turn off system. And because as I just mentioned, we don't have a background emission, so we can accomplish very high resolution. Okay, for ACQ system, you can't use too much. I will talk about that later. Okay, when you use too much, it will aggregate the emission is turned off. So you have to use a very, very small amount. When the amount is small, the signal is not strong. Plus, you have a very strong background, so the resolution will become poor. And for our system, we don't need to wash. If we make our AIEgen water soluble, okay, you don't have a background emission. Okay, so the wash process actually is easy to say, but very difficult to do. Okay, my friends in life science area told me that very often, student A and student B will give you different results. Why? Because student A probably did not wash to the right point. Okay, so you have false positive, but student B washed too much. Okay, so you have a false negative, because you don't know what's the right point. Okay, to which you should wash. For us, we don't need to wash if we make our AIEgen water soluble, so you don't have a background emission. Okay, and for AIE system, we can use a very high concentration. Just imagine what happens. Okay, there's a cancer cell here, and if we make our AIEgen positive charge, okay, so the electrostatic interaction will attract our AIEgen into the cancer cell, because inside the cancer cell, the mitochondrial membrane potential is very negative. Okay, so if you incubate for some time, more and more and more AIEgens will enter the cancer cell. Okay, of course, first of all, that will make the cancer cell very, very emissive. And secondly, when you have too many AIEgens inside the cancer cell, it will interfere with the metabolism process of the cancer cell. So that itself can kill the cancer cell. And in addition, when you do the imaging, actually, sometimes you can generate the ROS, okay, the reactive oxygen species. That will activate photodynamic therapy process to kill the cancer cells. So this synergistic effect make our AIEgen, very suitable for diagnostic applications. And our AIEgen is very stable. Okay, it's resistant to photobleaching. And sometimes people will ask me, hey, why your AIGen is so photostable? Actually, it's not because it itself is photostable, but because it's a nanoparticle. Okay, as I just mentioned, for conventional system, you have to use a very, very dilute solution. So they are molecular species. When you use a very strong laser beam to irradiate, okay, these few molecules in air, you will induce photooxidation. You will decompose the molecules. But for our AIEgen, it's kind of a nanoparticle. So you can bleach the molecule on the surface, but the inside we still have hundreds, thousands of molecules to emit light. So that is why our photostability is really good. We can do long-term tracking. Okay, the reason is because once it's internalized, it's very, very hard to come out from the cancer cell. Okay, but for a conventional system, because you use molecular species, okay, so inside the molecule, when the concentration of the dye is higher than outside, it will come out. Okay, but for our AI nanoparticle, but because it's endocytosis, once it's internalized through the endocytosis process, the interaction inside the cell will keep the nanoparticles inside. So that is why we can monitor the cancer cell for a very, very long time. Okay, nanoparticle is perfect. Okay, because our aggregate basically is a nanoparticle. But for ACQ system, because ACQ, aggregation consequential, you can't use nanoparticle. Okay, and another thing I didn't mention today is the Stokes shift. For conventional system, the Stokes shift sometimes are very, very small. Say, for example, for the body I just talked about, the Stokes shift could be just a few nanometers. Okay, so this will have a problem. Okay, you have a very strong self-absorption. Okay, and sometimes technically it's very hard to remove the excitation light. Okay, so you have a very, very strong background. For our system, the Stokes shift can be very, very big, can be hundreds. Okay, one or two or more than 200 nanometer Stokes shift. So you don't have self-absorption, you don't have a background from the excitation source. Okay. Okay, let me summarize what I have just presented. So basically, I talk about two parts. One is the fundamental study, and another is a practical application. I will try to finish soon, so leave some time for you to ask questions. So fundamentally, basically, we try to understand the structure of the AIEgen. So basically, the AIEgens are molecular rotors or molecular vibrators. Okay, so they can either rotate or vibrate. Okay, and the working mechanism is the restriction of intramolecular motion, or IIM. This is a very simple working mechanism. So you can imagine you can do many, many other things. Okay, say for example, today I did not talk about that. You can utilize this to monitor the Alzheimer disease, because the Alzheimer basically is associated with the formation of amyloid deposit. Amyloid is the protein fibers. Okay, so if the protein is water soluble, our stuff will not eliminate. But when the soluble protein form aggregates, it will wrap AIEgen inside the fiber, and then you can monitor this whole process. Okay, visually. In terms of application, actually, we have done a lot in the area of energy, environment, and health. But today, because the conference is focused on health, so I just presented some examples of the applications in the area of health. And if you want to know more, I give you some reference here. Okay, so for example, this chemical review paper we published in 2015. It's a very long review. It's 232 pages long. Okay, so if you read that review, you will know the overall picture until 2015. But of course, if you want to know new development, so we have a review published in CAM, published by Cell Press, okay, a few years ago, and we talk about the biomedical applications from organelles to animals. And these are tons of chemical research is published by the American Chemical Society. And we also talked about biomedical applications. This year is a 20th anniversary of AIE research. So Angewandte Chemie published a special issue to celebrate 20 years of AIE research. In this special issue, we publish a review, summarize the recent development in the area of AIE research. So if you are interested, you may read these new review articles. Okay, so now Sigma Aldrich is sending our AIE compounds. Okay, so you can see you can order from them, and I have built AIE Institute in Guangzhou, okay, in the science city of Guangzhou city, and this is the website of this institute. This institute actually is a company, okay, to sell many of our AIE products, and if you are interested, you can check this web page here. And my students in Hong Kong, okay, also have a small company called AIEgen-Biotech. Okay, so this is the product sold by AIEgen-Biotech. Again, this is the website, and if you want to order from this institute or this company, feel free to contact them. But if you need free samples, just send me email, and I will ask my students to send the free samples to you. Okay, finally, I talk a little bit about our new journal, okay, published by Winey. So this is a journal called AIEgen. It's open access, okay. So this we started this journal at the end of last year, and we have published many high quality papers. The first impact is predicted to be well above 10. Okay, so if you have a good research work, you are welcome to submit it to our new journal. Finally, I would like to thank my students. I was working at the Hong Kong University of Science and Technology until last April. Okay, so I moved to the Chinese University of Hong Kong in Shenzhen in April of this year. So in about half a year, I quickly assembled a research team with excellent students. Okay, so I'm very happy to work with them, and I thank them for their great contributions. So I will finish my talk here and leave some time for you to ask questions. Thank you very much for your kind attention.
Thank you very much, Professor Tang, for the wonderful talk. Let's thank our speaker.
Thank you.
Now, can take any questions?
Thank you, Professor.
Yeah. Is Zhong Liu from Nanjing. Can I ask a question?
Yes, please. Yes, please.
Very good. That enlighten us a lot on labeling. Although we are not in the field, we tend to understand a lot more. I have just a small question. We do a lot of particle emission, particle scattering. We tended to study some the fluorescent particles, but not that much of successful. But we're still trying. So is the particle, is it possible if we buy from the company you just highlighted in your last slide? If we buy the product, are we going to see the isolated particle, or are we going to see a bulk or something? What shape of this AIE is?
Yes. We can sell you the nanoparticles, but we normally we just like Sigma Aldrich does. They probably just send you the compounds. But if we need a nanoparticles, yes, we can we have this nanoparticle here. Okay. So if you want to have a lot of particles, we can send you a lot of particles. No problem. It's very easy.
Great, great. When you say nanoparticle, how large is the diameter?
It depends on your request. The particle size can be 100 or 200 nanometers. It could be smaller. It could be bigger. It depends on your request. What kind of size?
Yes, we just.
What kind of size do you want?
Well, yeah, we
What's the size?
For some 100, that is yeah.
I cannot hear clearly.
Well, we are trying to break in the different limits. So if it's 100, it's already breaking the different limits.
I cannot hear you clearly.
Yeah, maybe
you want to have another particle?
Oh.
Okay. So 10 nanometers or 100 nanometers? Hello?
Yes, that will be help us a lot.
So sorry, I cannot hear you. Sorry.
Yes, indeed. We are talking offline.
Okay, sure. Yeah.
I can talking.
Yeah. Please send me emails or we can chat through WeChat, through Weixin. Okay.
Yes, we can Weixin. Yes.
Okay.
Indeed.
Yeah, the organizer knows my WeChat account, so probably we can have a discussion through WeChat.
Yes.
Okay.
Okay, thank you very much. We have one question here from Glasgow.
Yes. Yes.
Hello, Professor Tang. Thank you for the beautiful talk and very impressive work. And my question is, you said these AIE genes are quite stable in ambient conditions. My question is, how about their stability and when the temperature increase?
Oh, yeah, that's a very good question. Okay. Okay, so you are talking about the molecules or you are talking about the particles, the nanoparticles?
Maybe both.
Okay, good. Okay, molecules are stable to temperature. Okay, now when we make nanoparticles, when you heat it up, several things can happen. Because once it's aggregate, okay, the temperature effect will be the following. First of all, it depends on whether the aggregate is crystalline or amorphous. Say, for example, if it's crystalline at room temperature, you heat it up, okay, to a certain temperature, it will undergo this morphological transition from crystalline to amorphous, okay? And normally our crystals are more emissive than amorphous. This is very easy to understand because in the crystal, the molecular motion is more restricted than in the amorphous state. Okay, so this in some sense give you so-called sensitivity or response to the temperature, to the thermal stimulus. Okay, so we can tune the brightness by changing the temperature. And actually, we can also change the color of the emission because crystal normally will emit in the blue region, amorphous will redshift. Okay, and right, and of course, if you heat it to too high temperature, it will melt. It will become liquid, and once it becomes liquid, it's no emission anymore. Okay, because in the liquid, the molecular motion will be too active, and that will completely quench the emission. Okay.
Yeah, thank you very much.
Okay. Thank you.
Okay, thanks again. Do we have any other questions? We have one more question here in Glasgow.
Yeah. And thank you for your great talk. And I have a question is, you mentioned about two imaging systems. It's AIEgen and another one. And you mentioned about the advantages of the aging system, and does it have any drawbacks? I mean, limitation of this system.
You mean the core share structure you are talking about?
You mentioned about the AIE imaging system, and you mentioned many advantage side of this system, and does it have any drawback?
Okay. Yeah, normally people talk about the advantages. Okay, now you ask what is the drawback of an AI system? Yes, that's one drawback. The drawback is that in the solid state it will emit light, but as you know that for many this kind of a commercial paper-based or strip-based sensors, okay. So once we put our AIEgen, once we deposit, let's say deposit our AIEgen to a paper strip, the emission is on. So this will force us to develop a turn-off system. This is a drawback. However, we can solve that problem. Okay. So what we do is that we can quench the emission of the aggregate by the structure design. So, for example, we can incorporate some electron accepting group or even electron donating group to the AIEgen to effect this so-called PET process, photo-induced electron transfer, and that will quench the emission in the solution state and also in the aggregation state. However, if the ionite, if the things we are going to detect can react with that quenching group or cleave the quenching group, then the emission will be turned on. So we can solve this problem, although this is a drawback if you want to ask me. Okay.
Yep. Thank you.
Okay, thank you.
All right, thank you very much again, Professor Tang. So we'll take now half an hour break. So meet you all in half an hour for the next block of lectures.
Thank you.